If you have ever used a cell phone charger to power up your phone, you have used a diode rectifier. Rectifiers are among the most common devices that you will find in any home today, and they are all based around the functioning of the junction diode. So let's understand how this device works in more detail. At the heart of most rectifier devices, you will find a diode, a junction diode, and here is the symbol for the diode. And this is the P side, and this is the N side. If we apply voltage like so, that is positive voltage on the P side and negative on the N side, this is what we call forward bias. And if we were to reverse the arrangement, that is, we are applying negative voltage on the P side and positive voltage on the N side, this is what we call a reverse bias. When the device is in forward bias, when you are biasing the diode in the forward direction, it is acting like a short circuit, which means that it is providing almost no resistance in the forward bias condition. On the other hand, if you put the diode into reverse bias, that is, you are applying positive voltage to the N side and negative voltage to the P side, the diode is turning into an open circuit. There is no majority carrier current and there is almost no current through the device, so it turns into an open circuit in the reverse bias condition. So what we have here is a device which is allowing current to flow only in one direction. If you reverse the direction of the voltage, there will be no current. And we can use this property in order to convert an AC signal into a DC signal. The reason we need rectification is that in most places, the power grid works on alternating current. And as we have already learned, alternating current is changing its direction constantly. It changes direction twice every cycle, and that is obviously not very useful for devices which require a non-changing current in a single direction which is stable, which is DC. So to convert AC into DC, we can use a device which allows only unidirectional, one-directional flow of current, and that is what a diode does. So how do we use this device in a circuit to achieve rectification? Let's see in detail. Let's say that we have a transformer. So here is my transformer. It has a primary coil, and here is a secondary coil. You will notice that the secondary coil is a lot smaller than the primary coil, fewer number of turns. Here we have the laminated core, and this is a step down transformer because here is the high voltage side and here is the low voltage side. That is why we call it a step down transformer, because it reduces the voltage of the incoming AC signal. Please remember, a transformer does not change the power level of the signal. So if you are reducing the voltage on the output side, you're also stepping up the current in equal proportion. In this case, the current coming in, or the voltage coming in more accurately, is AC voltage. So we will connect this to an AC source. Here is our AC source. And in India, the AC source is operating at a frequency of 50 Hertz. And 250 volts. Now 50 Hertz is AC, not DC, and it is at a very high voltage. 250 volts is not appropriate for most small devices we use at home. So we require the step down transformer to reduce this high voltage to a lower level of voltage. But it is still AC. We are still getting an AC output on the low voltage side. We have to convert this into DC voltage. Let's see how that is done. So what I do is I will connect a junction diode, a PN junction diode on the output side in this fashion. So here is my diode, and I'll connect this to a load in series. So here is my load. The load can be anything. It can be a phone, it can be a toy, it can be any device which requires DC power at low voltages. If we look at this using a graph, here is a graph. This is the waveform that we have. So this is one complete cycle. This is one complete cycle, and you can see that there is a positive half cycle and there is a negative half cycle. So here in the positive half cycle, this is the polarity of the secondary coil of the transformer. So we can see here that the polarity at the diode looks something like this. So right now, this diode is in forward bias because the P side has positive polarity while the N side has negative polarity. As we had learned earlier, when you forward bias a diode, it acts like a short circuit. It has no resistance. So as a result, for this half cycle, current will be able to flow freely through this device in the forward direction. So a load current will flow through this load. That depends on the output of the transformer secondary coil. But the moment we switch to the negative half cycle, so when we switch to the negative half cycle, the polarity changes. So the polarity here reverses itself. Now this is positive and this is negative, which means that the polarity at the diode will also change. So now we have reversed the polarity. So this is negative on the P side and positive on the N side. Now this diode is in reverse bias. In reverse bias, the diode is acting like a open circuit, like a broken connection. So in a broken connection or an open circuit, there is no current. So the current completely disappears for the negative half cycle of the incoming power, which means that this device is conducting only for a single cycle. If you were to compare the input and output voltages, you would see something like this. So this is the input and this is the output voltage. The input voltage is a full sinusoidal cycle, which is repeating again and again. But if we look at the output voltage, we see something interesting. Only 1/2 of the voltage is actually causing a current in the device. So here is our output value. This is the input and this is the output voltage. Now, this isn't really what we are accustomed to when we say DC. In DC current or DC voltage, the voltage and current remain stable. So this by itself is not a very useful output. It's all bumpy and rough. We require a smooth and unchanging value for voltage and current. To accomplish this, we have to ensure that during the reverse bias also, the current is being conducted only in the forward direction. In other words, we need forward current even for reversed voltage. To accomplish this, we use a modification of this circuit because this circuit is what we call a half-wave rectifier. And it is a half-wave rectifier because it is only rectifying half of the input AC waveform. We require a rectifier which will rectify both of the waveforms, the positive and the negative half cycles of the incoming waveform. So how do we do that? We do that by adding one more diode into the circuit. So let's look at a full wave rectifier now. So again, we will make a transformer, the primary, the core, the secondary. And again, this is the step down transformer. We have the high voltage side and the low voltage side. Now the change that we are going to make here is, instead of using just a single diode for our task, we are going to use two of them. So I have a diode here, and I also have a diode here. So this is diode D1 and this is diode D2. We also need to make a change to the secondary coil of this transformer. In the previous case, we noticed that there was only a set of two terminals for the output coil of the transformer. But here we are going to tap into the center of this coil and get a tapped output at this point. That is why this is called a center tapped transformer. So this is called a center tap transformer because of this feature. Now, why is this useful to us? We will see in a moment. So the load that you want to drive using this device is connected here. So this is our load. This can be anything. This can be a phone. This can be a toy. Any device which uses DC power, and we connect the opposite sides as well. Now, how will this device work? Well, for the positive half cycle, we will notice, or you will notice, that D1 is in forward bias, but D2 is in reverse bias. Which means that for the positive half cycle, so when the incoming waveform looks like this, diode D1 is in forward bias and diode D2 is in reverse bias, which means that diode D1 will act like a short circuit. It will allow the flow of current in this loop through the resistor, but diode D2 is in reverse bias, so it will be acting like an open circuit. There will be no current in this loop. So here is the input waveform. Here is the input waveform. But the output waveform looks different in the case of center tap transformer. If we were to compare the two waveforms using similar graphs as we did before. So here is the complete input waveform. The output waveform for the first half cycle looks something like this. But now, if we were to look at the second half of the input waveform, so this is the first half and this is the second half. In the second half, the polarity of the coil reverses. The secondary coil is now applying voltage in the opposite direction. This means that now diode D2 will be in forward bias while diode D1 will be in reverse bias. This means that diode D2 will conduct freely while diode D1 is an open circuit. So now you have a current in this direction through the resistor or through the load. You will notice that no matter which diode is activated, the direction of the current through the resistor, through the load remains the same. And this is vital because DC current means the direction of the current never changes. So if you look at the output waveform for a full wave rectifier with a center tap transformer, you will see something like this. So what we are observing here is that for both the forward and the reverse cycles, or for the positive and the negative half cycles, we have a positive current in the output. And that is what we require. This is still not a perfect answer because instead of getting a smooth DC output, we are getting something which is very bumpy. So we have to improve on this design. To do that, what we can do is we can add some extra components to make the waveform smoother. To do that, what we do is, across the output of the rectifiers, we place a large capacitance capacitor and then we connect the load. The capacitor will charge during the positive half cycle, and so this is the output being received by the capacitor. As the voltage here increases, the capacitor gets charged to full value. But as the voltage here decreases, the capacitor will try to maintain the same voltage because a capacitor shows the inertia of voltage. That is, it tries to maintain the same voltage across the load. So it will try to maintain the same voltage across the load as the input voltage is going down. Again, when the voltage increases during the second half cycle, the capacitor will start charging again, and as a result, it will have a smoothing effect on the output across the load. So if this is the output waveform from the full wave capacitor, this will be the actual waveform seen across the load. You will notice that this is a smoother curve. Large capacitors are used in things like power supplies specifically for this reason. We want to reduce the ripple in the circuit as much as possible.
Manorama Horizon. Learning made simple.